Welcome to the CNC Machining Workshop. I'm Matthew Mosier. I'm the lead CNCer, I don't know what it's called, at Code Orange, and these are my other presenters.
Hi, I'm Caden Davis. I'm going to be the lead CNCer next year for 5199.
I'm Connor. I was the lead CNCer 2019.
All right, so next slide. All right, cool. All right, so what is CNC machining? Some of you may not know out there. CNC stands for computer numerically controlled. Basically, what you need to know is that you have a computer with code on it that it sends off to the machine, and then the machine does whatever it does. It uses motors, and it spins its spindles, it cuts its parts. And there are a lot of different types of CNCs. The most common one for robotics would be CNC routers, and next comes like mills, CNC mills. But for robotics, the most important one would definitely be a CNC router. So any new, any team that doesn't have CNCing, any CNC like machines, and wants to go into CNCing, it would be recommended to get a CNC router because that's the most useful for making big plates. It can also do box tubing when you set it up correctly. So you can do a lot of pocketing and whatnot to make your robots better. And like I said, there are a lot of CNCs. Like a laser cutter is a CNC machine. A water jet is a CNC machine. But it's kind of crazy because any manual machine basically has a CNC machine. There's even like CNC. There's all kinds of machines. So next slide. So why would you actually want to use CNCing? Well, CNCing is very accurate when it comes to tolerances. I think at Code Orange, the router that we have it has a tolerance of 1,000th of an inch, and our mill, our CNC mill, has a tolerance of a 10,000th of an inch. So they are very accurate, and all your parts, if you set it up correctly, will come out exactly as you want them, and there's not going to be any problems, major problems. But they're also very efficient because so later on we're going to talk about the steps that you have to go through to create a part. And you do the first two steps once, and then you can recreate the part over and over by just doing the final two steps over and over. So they're very efficient when it comes to time and what you have to do. And also they're very efficient when it comes to like material, because you can set your parts that you're cutting right next to each other within like very, very close tolerances. So you don't actually have to waste a lot of material that you're cutting out of to make your parts. And obviously, they're probably faster than a normal person just trying to do it on like a manual mill or some other manual machine, because it's a robot doing it, basically. And you can set all your feeds and speeds correctly, and it will be running through your parts at high speed. Next slide.
To add on to that really quick, another important factor when considering the accuracy is the repeatability, because you are just repeating a set of machine code instructions. So you are able to make identical parts. Not only are they accurate, but you can make 40, washers that are all the exact same diameter within an extremely tight tolerance.
Oh, that's a good thing that go back just real quick. There's one important thing that I wanted to say that I ran into because I run our CNCs, was that you also have to make sure that what you're cutting out of, the parts, like the part blank and the stock that you're cutting out of, is within your tolerance as well, because we actually ran into a problem where we were like, why are our cuts off? But it's actually because the tubing that we had was way out of our tolerances. We just never read our tolerances. So if you're going to be CNCing, make sure that the stock you get is within your tolerances as well. That's just an important note. So, and technically 3D printing is a type of CNCing, but it's often like something that kind of competes with it, but they're very different in a lot of ways. So CNCing, obviously, you have usually a big just piece of metal or whatever you're cutting out of, and then you cut away to make whatever part. Well, 3D printing, you add to it, you're putting plastic down to make whatever part you're making, and like it says here, that it's typically a little bit more expensive because you're actually using metals instead of just using basic plastics, because it's very difficult and also expensive to get the 3D printers that use anything but plastic. So it's often better if you're making metal things, obviously, to use CNCs. And you can also use polycarb and whatnot on a CNC. And the major problem with CNCs is that it's very difficult to make very complex 3D things when you're cutting instead of just additive machining like it says here. So it's better for 3D printing if you're trying to make very complex things. And there are larger tolerances on 3D printing instead of CNCing because of like thickness of your plastic and whatnot. And it's important to like think of all the aspects of whatever you're making before you choose what you're actually going to be using. Yeah.
So the CNC workflow comes in 4 basic steps. First, you have to decide what parts are you going to be making using the CNC. And that comes from the CAD, which, as you guys most likely know, is computer-aided design. That's where you design all the parts for your robot. Then you switch to CAM. This is a product like SolidWorks CAM or Autodesk Fusion. This is computer-aided manufacturing. In CAM, you take the parts from your CAD and convert them into the instructions that the CNC, will run to make the part. Then you have your CNC setup, which is loading the material properly, making sure everything is correctly calibrated, making sure you have the right size cutting bit, the mill tool for the CNC. And finally, you have the CNC machining, which is where the machine actually executes all the instructions you have given it. And hopefully you produce a nice batch of parts.
I have one caveat to the computer-aided manufacturing, CAM. A really good CAM software that actually can just be added on to SolidWorks is HSM Works. We use it at Code Orange, and we've had basically no problems. There's some really good stuff you can do in that. So that's another CAM software you're able to use.
And to add to that, even at 5199, we use Autodesk Fusion 360 because we're used to it. We know it. We find it works for us. Yeah. So really everything, there's a lot of different great programs out there that are usually free. So this kind of expands on something we talked about earlier, the ease of machining different parts. So the parts you see on the left here are like the perfect parts for a typical CNC router. So a standard CNC router that would be accessible to robotics teams without hundreds of thousands of dollars are called 3-axis routers. They move X, Y, and Z, and that's it. So they are really good at making simple geometries, very good at parts that have 2 flat surfaces. So just basically flat parts for the most part. The 2 examples on the right, those are parts that would be like impossible or, well, basically impossible to produce with a standard 3-axis router. So the middle example, this is a complex pipe. So the reason that this would be impossible to make is because you wouldn't be able to carve out that bend in the material because your CNC machine can't kind of snake its way down. It can only access like certain surfaces. It can't access inside surfaces. And then the part on the right here, that lip that you see overhanging that would prevent a standard 3-axis mill from reaching that inner surface. You notice though that the machine there is able to cut it. That is known as a 5-axis mill. That is a kind that you can rotate the head of it to access more difficult to reach surfaces. But in general, that would be inaccessible for FRC. So here are we're going to introduce some vocabulary related to CNC and machining. So the toolpath is the name for the instructions that the CNC machine is going to execute. So you see on this path or on this cam here, that green path is the outline that the spindle, which is basically the spinning cutting bit, is going to follow as it cuts the material away. So it'll trace that line again, all the way down until the desired thickness is cut. Then our next term is the 0 point, also called the origin. It's just like it is in math. It's 0.000, where just x is 0, y is 0, z is 0. This changes depending on your team's preference. Like I know for our team, we put this in the front left of the sheet. Other teams might choose the back left, for example. It really is preference. You just have to make sure that you correctly calibrate your machine depending on what you set in CAM. Here are some of the common toolpaths we used. So 2D adaptive clearing is also very similar to that one at the bottom, 2D pocket. This is what you would use if you are trying to clear away a surface of material. For example, if you're trying to carve a 1-inch hole in a plate, a 2D pocket would go back and forth across that hole, shaving away the top layer, go over it again, shave away that second layer, and repeat that until you have carved out that hole. 2D contour is a bit different. In this, it traces an edge. It doesn't cut away an entire area. It only cuts around the edge. So an example of this would be just the outline of a part. Like let's say you're making a plate. This would be the outline of the plate because you would just trace along that edge to separate the plate from the stock, which is the material sheet. Our final one is bore. This is used for smaller holes. Think 3/16 or 1/8. In this, because you're carving away so little material, then the router's bit is able to just very quickly plunge into the material and just cut away that tiny amount. You would use a bore if the size of the hole you're cutting is pretty close to the size of your bit. And you would use a 2D pocket if the hole is a lot larger than your bit. So this is a CAD consideration to make when you are camming parts. Sharp inside corners are really difficult to machine because if you think about it, you are using a spinning bit that is basically a cylinder. So it's not able to produce that sharp corner without cutting into it more, as you see on the right. Just because if you go all the way up to that corner, then you have a round bit and that would leave a slight rounding on it.
I have one
caveat.
That if you're making something like this, you see here where it's a like a spacer or something. For something like this, what we do at a Code Orange is we actually cut a circular hole that's 1/2 inch. I think that's 1/2 inch. Yep. And then we use it's called a hex broach. It's a very useful thing that most teams should have if they're making stuff like anything that's that uses 1/2 inch hex rod, and it basically turns a circular 1/2 inch hole into a 1/2 inch hole for hexes. So that's a useful thing that we use at robotics.
To add on to that a tiny bit, if I recall, correct me on this, you need with the hex broach some kind of press, whether an arbor press or a hydraulic press, to punch the hole. Yeah. So when you lay out parts in CAM, you first of all want to make sure that your axes are correct. This is done by making sure your 0 point is in the right place and that your X direction, Y direction, and Z direction are all running in the directions that you want. For example, positive Z we set as the upward direction, and we just have to make sure we account for that in our CAM layout. When you are laying out all your parts, what you most want to do is maximize your efficiency and your yield, because it takes a lot of time to set up the CNC with putting on the material sheet, securing it, making sure it's calibrated, that you want to get as many parts as you can from a single setup of the CNC at a time. You also want to make sure you get as many parts as possible with as little material wasted as possible from your sheet of material. So as you can see in this example here on the right, we pack together most of the parts really tightly as we can, making sure that we don't set it so tightly that the bit will cut into the other part as it passes through. But we want to make sure there are no big blank regions where we could have fit another part and gotten more use out of the machine and out of that sheet. That just ends up going to waste because it really is just wasted money.
Oh, could you go back a slide? I just want to interject on the end of that. You also want to, when you're laying out parts, make sure that you don't make islands. You don't want to have an island of material that gets cut loose because that'll just kind of jump around in your bed. And that can end up breaking bit or whatever, jumping out and hitting something. So some more vocab words. We kind of introduced this earlier, but the stock is the actual sheet of material. In this case, that picture is of aluminum stock. The setup, we kind of say the CNC setup is the folder containing the G code, which is the set of instructions that the CNC machine runs. So in that little diagram there, on the computer, you produce the setup, and then using a flash drive or some other kind of file transfer, however you do it, you transfer that folder and the contents to the CNC machine where it executes those. So in your CAM settings, there are a lot of different settings to play with, but here are some of the most important ones. Your top and bottom offset. This tells the CNC's bit how far should it go down when it is cutting through the material, and how far above the surface of material should it go when it's moving. These are very important to set because so first with the top offset, if you don't set your top offset correctly, then your bit might not fully retract from a deep hole and end up breaking itself as you try to move out of that hole when you aren't fully out of it yet. For the bottom offset, you want to fully cut the material free from the sheet so that it's not connected by a thin layer of metal, because that leads to just burrs and makes it more difficult. But you don't want to go too far down because that'll cut into the board underneath the stock and damage that. The depth of cut kind of ties to that. That's how far should we plunge down to make sure we fully get through the material. And when managing all these different settings, I know at least for Autodesk Fusion, and I would presume for SolidWorks HSM Works, you can set defaults for everything. We have a default setup for 3/16 aluminum, a default setup for 1/8 aluminum, and so on, to make sure that all our settings are accurate and kind of standard. And if I can hop in on this one real quick as well.
Yeah.
A couple of times that you kind of see that you want to use these is we use our top offset because sometimes our material is kind of bent up in the middle, kind of bubbles up just from how it's set down. The bottom offset, sometimes our zero is a little bit higher and lower in different areas. The MDF bubbles up in a couple of spots. And
the MDF is the board underneath the stock, by the way.
Spoil board.
Yeah.
Could you run back just one more? And the depth of cut, that doesn't apply to everything. For us, it's just we have to use it because our end mill is a single flute. It's on a kind of low torque motor because it's mostly a wood cutting router, ours, and it's just modified. And we can't clear out a ton of material at once, just like you can with a full-size mill like Code Orange might.
Yeah, we have to kind of do multiple runs on a hole. Like we poke at it, get a bit deeper, come out, remove the chips, go again, cut the hole a bit deeper, and repeat until we hit the desired depth.
We do the same thing on our router, and on the CNC mill that we have. Usually we just go all the way to the bottom and we don't need a depth of cut. We just go straight through on the mill. But on the router, you definitely need a depth of cut because usually your bit is not good enough to just go straight through it. So
yeah, your bit will typically snap. So
you'll jam up and it'll just break because the motors will keep going.
Mm-hmm.
All right.
So cam simulation, once you've configured all your settings, made your toolpath, told it what to cut, you can simulate your cut where it'll draw a fake spindle, as you can see at the bottom there, and just kind of in cam run the cut on a sample stock and show you what your cut's going to turn out like. This is very important to do before you commit the time, the resources, the money, because it lets you just ensure that your cut is smooth, functioning as intended, everything is calibrated, and that you haven't missed any lines or selected the wrong operation for another line, for example. Yeah, just to make sure everything is smooth.
And this is also a really good spot to check for those little floating islands of material that can pop out. Because if you check to show stock and don't show the toolpath, you can actually see it like it would be once it's done cutting, like how your board would look at the very end. And you can see if there are any random floating parts that don't have a tab or whatever, or unsupported ends that you might need to worry about. And you can just go back and move things around to make it work right.
So post-processing is kind of the transition from CAM to CNC setup. In this, you have to configure a whole bunch of settings for your machine about, so for example here, NC extension .nc, that makes sure our code is compatible with our router. Really, all of these settings are just to go from the language of CAM, which is diagrams and CAD-like surfaces, to a toolpath and just generic instructions like move Y to, for example, on the actual router. So it's basically translating from CAM language, which a human reads, to CNC language, which the CNC reads. So in the normal operation of a CNC router, you need three supplies kind of commonly. You need end mills, which are the bits that actually do the cutting. There are a range of different sizes and a range of different flutes. A flute is kind of that groove you see where the bits, or where the little chips of metal get carried out. You need coolant. This is very necessary if you are cutting metals like aluminum, because they will produce sparks and other things that you don't want if you don't keep everything cool. Also, the coolant helps to keep the chips from flying everywhere.
At Code Orange, Code Orange, we don't actually use a liquid coolant for our router. We air cool our router, which makes it so we have to cut a little bit slower, but it also works. So air cooling a router is a possibility. We've been doing it for years, but if there's some problems if you use liquid coolants for us, but usually it's air coolant for just putting a ton of compressed air over our parts.
Yeah, a couple of things with the liquid coolant. The big thing is it just lubricates. It's like a cutting oil sort of thing. And but one of the biggest problems is if you use a MDF spoil board, it'll just get in there and the spoil board starts to kind of bubble up just because it's made of wood. It'll expand when it gets wet.
Yeah,
that starts to throw off your tolerances.
That picture is using a lot more coolant than what we would use in operation. We don't want a big layer forming of coolant on the surface of the material. We want just enough to keep things lubricated and cool without ruining our MDF or wasting coolant.
Yeah, with ours we just
yeah.
Go ahead.
I'm gonna get into the next topic, so if you want to finish.
I was just going to say the pictures of flood coolant, that's really good for mills and things where it's all in like one little unit. You don't have to worry about a spoil board. It's just on your material. And we just use a light mist, very, very light, of coolant.
The final thing that you need, hopefully this seems obvious, is the actual material sheets that you're going to cut from. So it depends on the team and on preference of how many material sheets you want to keep on hand and of what. I know at 5199 we like to keep a couple sheets, usually 2, 3, 2.5 around there, of 1/16 and 1/8 6061 aluminum, just because in a given night we could easily go through 2 sheets of that, and we don't want to be caught waiting on the metal suppliers when we're trying to make progress on a robot.
At Code Orange, we have a, I don't know, it's just a place we store all our metal and wood and polycarb, and we store a lot more of metal and polycarb. If I just like think about it now, we probably had like 20 or more sheets of metal there, but they're all different sizes and all of like different shapes and whatnot. And a lot of it's been used. So a lot of it for us is we just have a lot of material sheets at Code Orange.
Yeah, we have a cabinet with like 15, probably like 15 half-used sheets. If we're making just a couple parts, we'll throw those on, make sure we get our money's worth of the sheet.
All right, continue.
Yeah. Setting up a CNC router. So this kind of ties back to what we said before. You first load the material sheet onto the CNC board. In our case, it's the MDF spoil board. So when you load the material sheet, you want to make sure it's secure, because if you try to drill into something or mill into something that's insecure, then it will go flying everywhere, it will shake around, and it will likely break your bit just because the metal moving around is going to bend it. So we do this in 2 ways. On the back of the sheet, we apply a special double-sided tape to help the sheet stick down to the MDF board. But also along the edge of the sheet, we screw it down using, I thought I had a picture on here, using just cap screws. You don't want to use like a button head. You want to use something with as much surface area to hold down as much of the sheet as possible. Then you will zero the spindle. You do this using a little remote control. You move the spindle to whatever spot you want to set at 0, 0, 0. And then you click the set button and it's calibrated. Finally, you will set up whatever coolant method you have, whether it is air coolant. I know for us, we use the mist coolant, so we will turn on the pneumatic valve and turn on our coolant valve, wait for it to start spraying, and then we'll start our cut.
And real quick on the last one, some of them will just, you don't open the valve yourself. It's controlled by the machine, like some of the higher end mills and things.
Yeah. They'll
automatically just open and close their coolant. So it kind of varies machine to machine, yeah.
And here are some resources if you guys want to mark those down really quick. I'm gonna actually, oh, never mind. Here, I'll go back to presenting. Hold on, sorry. All right, there you go. If you guys just want to mark those down really quick, these are 3 sites I've found that are really helpful for introducing the concepts of CNC and a lot of the terminology you might find. If you guys want to present any questions you guys have in chat, we're open to answer them.
I've seen a couple pop up. One that I want to answer real quick because it was just at the end on the coolant topic is the difference between liquid and mist coolant. It's more of the difference between flood coolant and mist coolant. They're both liquid, but mist coolant is more of a spray bottle sort of thing. You're just giving it a little like fine layer of a coolant. Flood coolant, you're just shooting like a whole jet, like out of a hose. You're just in a ton of coolant, so everything's cool. Everything's covered.
Flood coolant is like pressurized liquid just shooting out, while mist coolant is introducing a little bit of liquid into a stream of pressurized air to kind of vaporize it and disperse it. I'm not able to see the question, so if you guys could share what you guys are seeing here.
I'll bring up a couple more.
Great.
Yeah. One that I just see is where do we typically purchase tools like end mills, and where do we find our feeds and speeds? Do you just want me to go at it with that one?
Go ahead.
I do the feeds and speeds thing.
Sure.
The end mills, you can get them off of a Master Car. You can get them. There are a lot of places to get them, really. I think ours are all off of McMaster. We use Onsrud, I think, is the company that makes them. But carbide, it's a kind of a joke, kind of truth. The Chinese carbide works really well. So you can get carbide, but really cheap from kind of anywhere. And feeds and speeds. Oh, do you want to go ahead?
Oh, yeah, you can go ahead. Yeah.
Okay. And on the feed speeds, that kind of varies depending on your machine's capabilities and your end mill's capabilities and your coolant and a lot of factors. I usually just start it low. With our router, the speed control isn't the best on the motor. And so I just spin it up to max speed and start at a low cut speed and gradually increase it